Good evening to all. Today we'll discuss Riemann integration. Okay. So here first we'll discuss in this partition. About partition, let the function f is a mapping from closed interval a comma b to R. We'll take. In this we'll assume this function is bounded as well as non-negative. Okay. And bounded means it should be exist infimum as well as supremum, right now. So if it should be satisfies both infimum and supremum, then that function we can say the function is nothing but bounded. And non-negative also we can take ma. And let this interval is nothing but closed. And here if suppose a is nothing but x naught, in this the elements are nothing but in this relation is less than, we are taking ma increasing function. A is equal to x naught is less than x1 is less than x2, so on xn is equal to b. That means in between a and b, we have the elements x naught. A is nothing but initial value x naught you should take, and this is x1, x2, so on xn is equal to b. Okay, and the finite set, this p is nothing but we are saying partition on this interval a comma b. Okay, and the n subintervals are there. So here we have x0, x1, x2, so on xn. N elements are there. In these the intervals are nothing but can divide, because a to b, this is interval, closed interval. In between a and b we have x0, x1, some finite number of elements are there. Okay, so these elements ma, from this we can divide finite number of intervals. Okay, x0, x1 is one interval, x1 to x2, x2 to x3, x3 to x4, so on, xr minus 1 to xr minus xr, and xn minus 1 to xn. So finite number of subintervals we can take here. Okay, these are nothing but called as segments of the partition P, or components of the partition P we can say. Okay, so here rth subinterval, here rth interval we are saying no. So rth subinterval is nothing but IR we can denote, and that is nothing but XR minus 1 comma XR. Its length is nothing but upper limit minus lower limit, that is XR minus 1. So that interval means length of the interval is nothing but we can denote with these notations, either delta R, this delta R, this can be also called as delta R only. Its length is nothing but difference between these two values, that is upper value minus lower value, XR minus 1. Okay, that means here delta 1 is nothing but here subinterval P1 is equal to x0, x1, P2 is nothing but equal to x1, x2, so on, PR is equal to xr minus 1 comma xr, and Pn is nothing but xn minus 1 comma xn, right now. So its lengths are nothing but delta 1 is equal to x1 minus x0 we can write, and P2 length of this interval is nothing but delta 2, that is nothing but x2 minus x1. So delta, so on delta R already we discussed here, right now xr minus 1. Okay, and delta n, nth subinterval is nothing but its length ma xn minus 1. So length is nothing but we can define like this. Okay, yeah. So the maximum of the lengths of the subintervals of the partition P are the maximum of delta 1, delta 2, delta R, delta n. This delta 1 is the first subinterval length. Second subinterval length is delta 2. So on rth subinterval length delta R, nth subinterval length is delta n. These are called as norm of the partition P. Okay, and the closed interval a comma b can be partitioned in many ways. the set of all partitions on closed interval a comma b is nothing but denoted as phi of closed interval a comma b. This is nothing but called as set of all partitions on closed interval a comma b. And here, if suppose two partitions you should take, here P1 and P2, these two are nothing but elements in phi of closed interval a comma b, means P1, P2 be two partitions on the set of all partitions on closed interval a comma b. Then here P1 is nothing but contained in P1 union P2, and P2 is also contained in P1 union P2. This means here P1, P2 is nothing but called as common refinement of P1 and P2. Okay, so here delta R is always less than or equal to norm of the partition P. So here upper and lower Riemann sums, these are many most important definition. Let F is nothing but upper and lower Riemann sums we'll discuss. F is mapping from closed interval a comma b to R. Here F is nothing but bounded on this interval, and it is bounded function we are taking, no? P definitely we have to take, that is nothing but partition. A final set P is nothing but said to be partition on closed interval a comma b. F is bounded on this interval, as well as F is also bounded in each of the subintervals of closed interval a comma b. Yes, ma'am. Now capital M and small m will take, ma'am. Here capital M is supremum and small m is infimum of the function f on this interval a comma b. Okay, here capital M r and small m r, these two are supremum and infimum of the function in the rth subinterval, that is IR equal to xr minus 1 comma xr, where r values from 1 to n. Okay, so capital MR is nothing but supremum, small mr is the infimum here in this interval xr minus 1 comma xr. So the sum is nothing but here capital M1 delta 1 plus capital M2 plus into delta 2 plus so on capital Mn delta n. Sum of this is nothing but simply we can write summation capital MR delta R. Here R values from 1 to n. This is nothing but called as upper Riemann sum, or it can be called as upper Darboux sum also of the function f corresponding to the partition P. Okay, and it is upper Darboux sum or upper Riemann sum is nothing but denoted as UPF or UFP also we can write. And the sum small m1 delta 1 plus small m2 delta 2 so on small m in delta n, simply we can write summation small mr delta r. Here also r values from 1 to n. This is nothing but called as lower Riemann sum or lower Darboux sum of the function f corresponding to the partition P. And here also lower Darboux sum or lower Riemann sum is nothing but denoted as LPF or LFP also. Okay? Yeah. In the previous month we discussed about the Riemann sum, upper Riemann sum and lower Riemann sum. Right now we'll do one problem by using that method, ma'am. So if f of x is equal to x has given on this interval 0, 1 and partition has given here 0, 1 by 3, 2 by 3, 1. We need to find here UPF means upper Riemann sum, LPF means lower Riemann sum. Okay, we'll find those two. And given partition is nothing but what is there? 0, 1 by 3, 2 by 3, 1. Yes, no? We'll write first of all subintervals. So subintervals means in between here 0 and 1, 0, 1 by 3, okay, 1 by 3, 2 by 3 and 2 by 3, 1. So how many subintervals are there? 3 subintervals. Those are I1 is first one 0, 1 by 3, I2 is 1 by 3, 2 by 3, I3 is 2 by 3, 1. These are the subintervals of closed interval 0, 1. And here lengths also you should find. Length of the subinterval of I1 is upper limit minus lower limit na 1 by 3 minus 0. 1 by 3 minus 0 is 1 by 3. And length of the subinterval I2, that is 2 by 3 minus 1 by 3. That should be is equal to 2 minus 1 is 1 by 3 only, 1 by 3. and I3 also, its length is nothing but 1 minus 2 by 3. 3 ones are 3 minus 2, 1 by 3. So here length is same, 1 by 3, 1 by 3, 1 by 3. Okay, and here we have supremum and infimum. Supremum is nothing but capital M1, capital M2, capital M3 corresponding these subintervals. So M1 is the supremum in this interval 1 by 3, infimum is 0. M2 is the supremum second subinterval ma 2 by 3. Infimum is 1 by 3, and M3 is nothing but supremum in subinterval I3, that is 1, and infimum is 2 by 3. Okay, so upper Riemann sum is nothing but denoted as UPF right now. So it can be written as capital M1 delta 1 plus capital M2 delta 2 plus capital M3 delta 3. So here only we have 3 subintervals. So we have 3 some of the values are there. So substitute, we have all the values no. So M1 is nothing but 1 by 3 and delta 1 is nothing but length 1 by 3 plus M2 is 2 by 3 and length is 1 by 3 and M3 is nothing but 1, delta 3 is also 1 by 3. Simplify this, 1 into 1, 1, 3 3s are 9 plus 2 1s are 2 by 3 3s are 9 plus 1 into 1 by 3 is 1 by 3. So here what is an LCM? LCM is 9. Okay, and here 3 3s are 9 means 3 into 1 is 3 plus, sorry, here 1 plus 2 plus 3, 3 plus 3 is nothing but 6 by 9. 3 2s are 3 3s are 9. 2 by 3 we should get. This is the upper Riemann sum. Okay. Similarly, lower Riemann sum LPF, that should be, we can write M1 small m1 delta 1 plus small m2 delta 2 plus small m3 delta 3. Here small m1 is nothing but infimum of this subintervals 0 into delta 1 is nothing but 1 by 3 is there plus m2 is nothing but 1 by 3 and delta 2 is 1 by 3. M3 small m3 is 2 by 3 and delta 3 here 1 by 3 is there. So again simplify, 0 into 1 by 3 is 0 only. 1 into 1 by 3 into 1 by 3 is 1 by 9. 2 by 3 into 1 by 3 is 2 by 9. So here LCM is 9. 1 plus 2 is 3. 3 1s are 3. 3 3s are 9. So 1 by 3. So what we are getting here? Lower Riemann sum is nothing but 1 by 3. Upper Riemann sum is nothing but 2 by 3. Okay. This is the example for upper Riemann sum and lower Riemann sum. Lastly, in this we'll discuss oscillatory sum. Okay. So oscillatory sum means difference between upper Riemann sum and lower Riemann sum is nothing but called as oscillatory sum. So that is f is a mapping from closed interval a comma b to R. Here f is bounded function as well as here P is the set of all partitions on closed interval a comma b, and I am saying no difference between two Riemann sums upper and lower, that is UPF minus LPF is nothing but called as oscillatory sum of the function f corresponding to the partition P on closed interval a comma b, and this oscillatory sum is nothing but denoted as WPF or OPF. Okay, so here WPF is nothing but or OPF is nothing but equal to UPF minus LPF. This is the oscillatory sum. Okay.